In this video, we're going to begin the transition from probability to statistics. So we've been talking a lot about probability and random variables and all these distributions and everything that goes along with them. But now we want to kind of shift over to the statistical side. But in order to do that, we have to have at least an idea of this concept of a sampling distribution. Right. So that's what we're going to define now, and just kind of give you a very brief idea of what a sampling distribution is and some of the key properties, and then in subsequent videos we will build on these ideas. So let's say we have a certain number of random variables, and it could be of any type, right? Even types we haven't talked about. So let's say you have x1, x2, ... Let's say that these are all random variables, right? So these are random variables. And they don't even have to be of the same type. In other words, let's say x1 could be a discrete random variable. Maybe it's binomial. And then maybe x2 could be a continuous random variable. Maybe it's a gamma random variable or a normal random variable. So it could be any sort of combination of these. And then what if you then decide to start doing arithmetic, or maybe I should say functional operations with these random variables? So like, what if you start to add them or square them or take the square root of these whenever possible, right? So a sampling distribution is, again, very, very general, right? So it is a function, right, of these random variables. So of these random variables. So it's something like this. I'll just call it like G, and then it's of x1, x2, ... xn, right? So again, this is kind of the very generic way of defining a sampling distribution. Now, if each of these are random variables, then it means the sampling distribution is also a random variable, because if I don't know specifically what the values of each of these random variables are, then I certainly wouldn't know the value of any combination of them, right? So this, in fact, is another random variable. Just abbreviate that to RV. So then the follow-up questions would be something like, okay, well, what type of random variable? Right? What type? And when we say what type, it's like, okay, is it going to be continuous or discrete? What is the distribution? So like, what is its distribution? Let's say, for instance, they're all normal. Is the combination going to be normal? Let me fix this right here. So what is its distribution? Etc. Like, can we find its mean? Can we find its variance and standard deviation? So in general, these are very, very difficult questions, right? Now let's add a bit more terminology to this. Let's say we avoid the situation where they're all different, right? So let's say that they're the same, right? So we would say that they're identical, right? So identical in this situation means that all the xi, they follow the same distribution. So follow the same distribution, right? Again, in other words, they have the same probability distribution. They can take on the same possible values. So they're basically the same. They're just copies of each other, right? Independent That's a concept that we have used quite extensively in the past, and independent means the same thing, right? So that the whatever happens with the first random variable is not going to affect the likelihood of any of the outcomes on the other one, right? So I'll just say means the same as it has, right? So it means the same. So if we make the assumption that these are all identical and they're all independent of each other, we pretty much say something like this. This is the nice little abbreviation we've come up with. We say that the xi's are IID. So they're identical and independently distributed, right? So IID stands for identical and independently distributed. So I guess you say identically and independently distributed. Right, and having these two assumptions will actually make the math a lot easier. If you just think about independence, when we introduced the concept of independence, it actually simplified a lot of probability questions that we had. Same thing will come up here, right? So when you hear they say, oh, we have a set of random variables that are IID, this is what it's referring to. All right, so what does this actually look like? Well, let me give you a discrete example of this and just show you what we mean by, I'll give you just two, right? So we're just going to look at two IIDs, and then we're going to look at a really simple distribution of these two, right? Sampling distribution of these two. So let's say that X is discrete and it has this very simple PDF, right? So let's do this. Let's say it can take on values of 0 and 1, and with probabilities, let's say this is 0.3, and then let's say this is 0.7, right? So let's say that x1 and x2 are IIDs of this distribution, right? So are IIDs of X, right? So basically, they're exactly the same, and it's almost like we're kind of doing the experiment or running our trial twice, and again on each trial we can either get a 0 or 1, and here is our probability. So here's a really simple distribution of this these two IIDs. What if we were just interested in the average, right? What if we were interested in the average? So let's this G that I just referred to, and this would just be a function of these two. What if we just take the two values that we've observed and find their average? So let's see if we can figure out what the distribution is of this. Let's see, if we can find the PDF of this, because once you have the PDF, you know everything about a random variable, okay? So how would we do something like this? Well, we basically, again, to come up with the probability distribution function for any random variable, whether it's discrete or continuous, we first have to figure out all the possible values of X, and then we have to come up with the likelihood or the probability of all of them. All right, so here's what we're going to do. Because there are only two, we can sort of visualize this using a nice table. Tables are so much fun. And then I'm going to put x1, let's say, as the rows, and then let's say x2 as the columns. It doesn't really matter. And then I'm just going to say, okay, because they're following the identical distribution, x1 can either be 0 or 1, and x2 can be either 0 or 1, which means then there are basically four possibilities, right, or four simple outcomes as far as the average is concerned, right? So I'm just going to put the letter G here to say, okay, we're going to be performing this function with these possible values of x. So if both x1 and x2 are 0, then that means the average would be 0, because you'd have 0 plus 0 divided by 2. So you'd have this. If x1 is 0 and x2 is 1, then the average will be 1/2, because you'd have 0 plus 1 divided by 2. So I'll just put a half there. And then we would get the same average if x1 is equal to 1 and x2 is equal to 0. So we would have 1/2 there. And then if they're both 1, then the average is 1, right? So now with this really simple situation, right, we have two IIDs that follow this distribution over here. Here are all the possibilities. So we know the sample space. So I'm just going to say, I'm going to write it like this, or sample space of G is this. We can only observe values of 0, 1/2, and 1. All right. Okay, so now that we know the possible means or averages that we can observe, then what are the probabilities, right? So let's see, what is the probability that the average, in fact, let me just go ahead and use this notation for the average, right? You might remember that that notation. If you've had other previous courses in statistics, you might know this is just a way of representing the mean, right, or the average. So what is the probability that we will get a 0? Well, look at it. The only way that could happen is if both x1 and x2 are 0. So we have and this probability that x2 is 0. And then this is essentially a probability involving an intersection. And because we're assuming independence, this is where it gets really helpful. So we can say this is the probability that x1 is equal to 0 times the probability that x2 is equal to 0. And I know both of those, and they're equal, and that they're both 0.3. So we're going to end up having 0.3 times 0.3, and that's 0.09. So there's a 9% chance that if we have our sampling distribution being the mean of these two, right, these two IIDs that follow this distribution, that we will end up with a mean of 0. All right, so there we go. And then we continue doing that, asking ourselves, well, what is the probability that, let me do this. Now, when let's look at the other possibility now, the probability that the mean is equal to 1/2. Well, there are two ways that can happen. That can happen either x1 is 0 and x2 is 1, or it's flipped. x1 is 1 and x2 is 0, right here, this possibility and this possibility. So I'm going to write those down, and because those are mutually exclusive, we will end up having this, the probability that x1 is equal to 1 and the probability that x2 is equal to 0 plus the probability that x1 is equal to 0. And, let me put the and in parentheses here. Actually, I think let me take this off. There we go. Let me fix this all together. I think I got carried away with my p's and parentheses there. So the probability that x1 is equal to 1 and x2 is equal to 0, like that, and then or the probability that x1 is equal to 0 and x2 is equal to 1. And again, because of independence, we can break this up. So this will tell us, so the probability that x1 is equal to 1, that's 1/2. So, I'm sorry, no, that's 0.7. So 0.7 times the probability that x2 is equal to 0, that's 0.3. And then in the other possibility, it's flipped, plus the probability that x1 is equal to 0, that is 0.3, times the probability that x2 is equal to 1, that's 0.7. So we end up having 0.21 here and then 0.21 there, so 0.42. All right, so we have this. Now, if you think about it, we only have one other possibility. So there are a couple things we could do here. We could use the complement rule and say, okay, we now know the probability of these three things happening. So the probability of the last possibility is 1 minus that. So we could add these two probabilities together, and that will give us 0.51. And then we would subtract that from 1, that would give us 0.49. So that will be kind of an efficient way to do it. But again, just to emphasize the IID property, let's go through and calculate it the same way and show that we will get the same 0.49. So the last possibility here is that our mean is equal to 1. That will only happen when both our random variables are equal to 1. So the probability that x1 is equal to 1 and x2 is equal to 1. And again, because of independence, we can multiply, and let me just kind of remind you. So we're looking now at the 0.7. So we're taking the probability of x1 equals 1, that's 0.7, times another 0.7, and then that gives us what I stated earlier, the 0.49, right? So then we can put this all together, and these are nice discrete values. There are only three possibilities, 0, 1/2, or 1, and we now know the corresponding probabilities. So here is the PDF of our mean. So I'm gonna just do another table, and now I'm gonna say x bar, and then this would be f of, well, actually, let me use the little x here, because these are our possibilities like that. And then we know we can get either a 0, a 1/2, or a 1. And then here are the corresponding probabilities: 0.09, 0.42, and 0.49. And even though it took a little bit of work to get this PDF is still a PDF, and it has to satisfy all the properties. So check your non-negative property, check the fact that the total probability has to be equal to 1, and you can see that it checks both the boxes, right? So that's a really simple example of a sampling distribution. So you can see a couple of things are important here. First, it depends on what we decide to do with our random variables. And here I just decided to compute the mean, right? But there are other things you could do. You could decide to maybe double x1 and then triple x2 and then subtract them or something like that. Or you could decide to square them, add, and then take the square root, maybe like a calculation that sounds like finding the hypotenuse of a right triangle. So there are lots of things you can do with these, but the thing is, the more complicated the function is, the more work it will take to find all the possible values and all the associated probabilities. But if you assume that the random variables are identical, if you assume that they're independent, then it simplifies things. The other thing too that can complicate it is, instead of having 2, what if we had 20? Imagine if we had 20 possible, even of this type, with the same distribution, right? Let me go back up. So if we had 20 of these random variables, all identical, all independent, and we wanted to know like the distribution of that average, a simple table like this wouldn't be that practical anymore. It would be a lot more complicated, right? So I just wanted to introduce the idea of a sampling distribution. And then in subsequent videos, we're going to talk about a few more specifics in terms of types of sampling distributions, and then how do we go about finding things like mean and variance and standard deviation. So there's our intro, and I'll see you in the next video.